We are two of many Railgun contributors that are here at the conference. Thanks for joining us for this little workshop. We're going to be talking through a couple things related to some of the prompts that we have bounties for the hackathon. The first is, I guess they're in reverse order. We're talking about private DeFi using the Railgun cookbook, which you can use to create any kind of private dApp from an existing dApp. You can make it private using the Railgun cookbook. And second, we'll be talking about private governance and how one might construct a system to do private voting for a DAO. Cool, so we're going to dive in to the cookbook a little bit. The cookbook is a SDK that was created by Railgun contributors. It's fully open source. The purpose of the cookbook is to abstract some of the difficulties with creating cross-contract calls using a private balance or a private Railgun balance. You can take that private balance and you can either swap, using one of the recipes here, you could add liquidity in terms of like LP. You can deposit tokens into a vault. You can do basically anything that you can do in DeFi with a private balance using a cookbook recipe. It's organized into these kind of recipes, which is a full contract call. That's the output you get. And recipes are made up of steps that have inputs and outputs and can be organized kind of in series. So the outputs from one step become the inputs into the next step, and they kind of flow onward. So if we look at kind of what it looks like to create a new recipe, I think we're going to look at a recipe for adding liquidity to Uniswap v2. Which is demonstrative of kind of the ins and outs. There's a few, I guess, sections to this. At the end, we're going to come up with a recipe, but before that, we will have intermediary steps to get some of the other pieces going. So every contract, every Solidity contract, when it is transformed from Solidity code to like an interface, that file is in JSON called an ABI. For liquidity, we have a few. The only one you really have to know about here is for the Uni v2, what we call like pair. Can you see this? Where there are a lot of Uniswap v2 clones. SushiSwap is an example, QuickSwap, PancakeSwap, and they all use the same contract calls, the same ABI. And so this Uni v2 like is like basically any clone of Uniswap. It'll have the same structure, the same calls, slightly different, well, it'll have different contract addresses, slight variances of which tokens are available to provide liquidity or to swap. But they have the same structure, and so we have this Uni v2 like pair. This is the ABI. Again, this is output from the Solidity contract, and so this is something that the contract essentially generates. We start with that JSON file here in the ABI section, and then we create a wrapper for the actual contract calls. So that ABI is sort of the skeleton. The contract call is the kind of the interface. So that we can actually call the blockchain through an RPC or another endpoint. So we have a Uni v2 like pair contract, right? It's basically the contract version of that API. The code here is relatively simple. We have a this is the Ether's contract object, which is of type Uni v2 like pair. You can generate these types through something called type chain, and there is, if you're working in the cookbook, I would suggest cloning the repo so you get all the files and all the the resources. There is this gen type chain script. So this would be something you run in terminal, gen type chain, and that will spit out the contract classes for each of the ABIs automatically, if you put them in the right folders. And so when you go in to create the contract class, it'll have the type chain types here. This is an auto-generated file from the ABI. It comes directly from that, and it will have all of the functions and all of the types for TypeScript pre-generated. And so it's pretty nice. So when we come in here, for example, liquidity is a little bit interesting in terms of the math. It gets a little bit complicated, and we're not really going to talk too much about how the reserves work or how the kind of on-chain, it's basically math between the reserves and the supply of each token to determine the price and to determine how much the price will move if you add liquidity on either end, how much of token B you need to add given a certain amount of token A. It's all based on, relatively basic division, but we're not going to talk too much about that here. But you do need to get a few, or have this data available, and so you can call the functions. These are view calls, so you don't spend any tokens like to call this. You can call it at any time, kind of through the RPC, and it will get these values, the reserves of token A and token B in the liquidity pool, and then the total supply. KLAS is another variable we're going to need to calculate some of the, as I said, supply 100 DAI. Well, how much wrapped ETH am I going to need to put them both in the pool at equal values? So the cool thing I want to show you here is if we're going to rewrite this function, we got this.contract. You can see all of the functions that came out of the ABI. So we'll do get reserves. You can see that it already comes with the types, it returns a promise. So we could say reserves here. You can see we've got types here. We can see that one has reserve 0 and reserve 1, and format it like this. We call it reserve A and B in here because we call it token A and token B. When you put up a liquidity pair, there's always 2 tokens, and you put up an equal value of each based on the reserves in the pool, as I said. So these are the basic contract calls for a Uniswap pair to get the values that we need to construct a contract call that we can issue an add liquidity request. I think we add it here. Yeah, so this is the other contract. There are multiple, many of these on-chain systems have multiple contracts. So you may need multiple ABIs, and it works all in the same way, right? So this UniV2-like router is another ABI. We can find that JSON, right? This is another ABI that the contract would output. You can typically find these ABIs. They're sometimes hard to source. You can typically find them on the GitHub of the project that created the contract. They typically publish them, or maybe in some of their front ends. You can trace them down, or you can build them locally with using Solidity or using their Solidity source code. So we have the router that generates this router type chain file, right? Using yarn gen type chain, that'll automatically generate this. This contract these are not view calls. These are actual transactions that we're going to call on the contract. Rather than getting data, we're going to be pushing data, sort of like a post call if you're familiar with HTTP. This one, for example, we are going to populate a transaction. This will give us the call data that is required that you could issue from like a 0x, your public address. You could use that call data to issue an add liquidity call with these fields. That's going to be packaged into our private transaction in the end, so we need this call data referenced here. Populate transaction, you can see, well, it returns this type, contract transaction, which is, again, the to field. This is the contract address. Data, this is the call data in bytecode. You're not going to need from, but that's another available field in this type. So we call this contract, add liquidity. It will tell you, I mean, you can see there's a ton of different types that this requires. These are the parameters for this function call. When we first type it in, populate, you can see it here. It needs token A, token B, how much of token A is desired, how much of token B is desired. We need to use the math to calculate that out. The minimum amount of token A and B, so this is because anything that uses one of these decentralized exchanges, you always pass in a slippage value. If you're used to actually trading on Uniswap, it's typically set to 1% or whatever. If the price changes between the time that you submit that transaction and it's mined, you want the transaction to fail if the price has shifted above that slippage value, right? You don't want to overpay for tokens just because of wild variation in price. It's the same thing with providing liquidity, right? You say, I want to provide $100 worth of DAI and $100 worth of wrapped ETH. If one of those shifts around dramatically, the price action is actually going to determine, how much of the tokens you put up. And so maybe your slip is at 1%. $100 worth of DAI is okay. I'm okay with providing whatever would be it. The minimum would be $99 worth of wrapped ETH, right, with a 1% slip. And so that's where these minimum values come in here. We've got a 2. I think that is that the destination? Yes. Yeah, so a destination address, which will almost always be your own address. When we talk about a destination, you're receiving what's called an LP token. You deposit 2 tokens in, and you get an ERC20. The contract address for that ERC20, it's just a normal token. It represents your position, and you can use it to withdraw those 2 tokens based on their current rate. And so as the rates change, your LP token may be worth a little more DAI and a little less wrapped ETH, right? That LP token goes back into your account, and you can actually, it has value. It has street value or whatever. You can trade it. You could swap it. You could sell it off, or you could send it to a different account, and they could withdraw it. It is totally, it's fungible. And just represents that position. So the 2 address would be who's going to receive the LP token at the end of this transaction, and then a deadline for it to get mined and execute. So the deadline and the minimum amounts are kind of parameters around the call to make sure that it's going to be executed in a timely manner. So this is, again, this is the skeleton now. Now we have contract calls that we can input a good amount of data that we have to kind of format, and this will give us the call data that we could execute on chain with a public address. This is really important because it's going to be packaged into, kind of sandwiched between these 2 actions in the RAILGUN contract. A transaction like this gets executed on a adapt module, so it's a separate contract from core RAILGUN logic. That adapt module allows you to take your RAILGUN balances, which are private and encrypted in the RAILGUN smart contract, available on Ethereum, ETHRome, Polygon, and Binance Smart Chain, as well as a few test nets. It unshields, meaning it withdraws some tokens that you designate from the private balance into this relay adapt contract. That's the first step. The second step is that it executes the recipe, the call data that, for example, this contract transaction with the 2 in the data field. And the third step is it takes the result from that call, so the LP token in this example, and it shields it back into the private balance. And so that whole circuit, it never touches a public wallet that you own. So that's what makes it anonymous and private. It all happens on chain. It's interestingly auditable because the unshield, these actions of coming out of the Railgun contract and going back in are public and on chain. They do happen, like the Uniswap contract needs to know what tokens it's receiving in order to give you an LP token. That can't be end-to-end private because Uniswap is a public decentralized exchange. But because of the properties of Railgun, it could have been any Railgun user that initiated that transaction that was holding those tokens, right? It could be anybody, and that's what gives it anonymity. When we go from kind of the setup stage of putting in the ABIs and creating the contract, now we're going to create steps. We'll create a step, add liquidity step. Here's an example. There is an abstract class for each step. You won't need to worry about what this is doing exactly, but when you create a new step, for example, I'll just demonstrate this part. New step. We'll do new step extends step, right? Import that class, and it'll automatically give you the required outputs. We can set up a config. I have GitHub Copilot on here, so it just auto-filled all that. New step description, so we can fill all that stuff in. So this is an interesting one for the add liquidity recipe. It's unique to decentralized exchange recipes that exist in the cookbook today. This field has non-deterministic output. That basically means does this have slippage? Do we have an exact value we're going to get from the contract or not? Do we know the exact value? So with this LP token, we don't necessarily know the exact value we're going to get because the price might slip. So this would be true in this case for the LP recipe. And then the next thing you have to figure out is get step output. So as I said, the steps are layered, or you can layer multiple steps kind of in series. The outputs from one step become the inputs into the next step. So each step doesn't really care what recipe it's a part of. It really only knows what are the inputs I'm receiving so that I can tell you what the outputs you should expect, right? We're going to just set up the return value. It's an object. Here. It is an object. It's got a few required parameters, cross-contract calls. That's the call data I was talking about. Output ERC20 amounts, output NFTs. NFTs work with this entire process as well. You can have an NFT shielded into your Railgun balance, unshield it into into the Relay Adapt contract through a recipe, and maybe swap it privately or whatever DeFi activities use NFTs. So we are going to create the cross-contract calls. We're going to show any output amounts. These are newly created tokens because of this recipe. Output NFTs for this example will be an empty array because it doesn't generate anything. There are some other ones. Fee, amount recipients. I don't think we need that one. Let's see. Spent NFTs, yeah, we won't need those. Spent ERC20 amounts, that one is, these ones are necessary. So this is the call data, call in to data from the contract call. Output ERC20 amounts, newly created tokens. So this would be the LP token. Output NFTs, not necessary. spent ERC20 amounts. For LP, like adding liquidity to an exchange, we're going to spend, let's say, the DAI and the wrapped ETH, and we receive the LP token to represent that position. So this will be, we call it token A and token B, right? These are going to be spent. And then fees. I think in the case of, I think we pre-calculate these, so I don't think they're necessary in this recipe, so we can get rid of those. And now, now that we can see the kind of the structure of what we output, I'll demonstrate kind of what the code is doing here. So, let's see. This is the constructor that will set up a few fields. For example, I showed the config with the name and the description. This will set up based on the name and description they don't really do anything. They're just kind of for debugging purposes. But we set the fork name, meaning is it Uniswap, is it SushiSwap, PancakeSwap? We set that up in the name and description based on the data that's passed in. We're going to need a good bit of data passed into this step, passed into the recipe in order to format those contract calls. And so that there's a type that we created here that has the amount of token A, the amount of token B, the expected amount.
We've lost the screen for a bit. So
yeah, are there any questions so far while we're working on AV?
Fees are the same, like withdrawals. Like when I withdraw from RAILGUN, it's 0.2 directly. So when I deposit withdrawals, the same.
Yeah, so that's a great question. So the question was about fees from RAILGUN. So yes, it's a normal unshield that occurs in this contract call. It is executed as a multi-call, so it all happens in one transaction. But it does do a normal unshield, and there is an unshield fee, and there's a shielding fee for the token that goes back into the private balance. There's a fee out, and then there's a fee back in.
Because it's ERC20,
That's right, yeah.
and for UniD3, it's an NFT.
Yeah, with UniD3 it is an NFT. It's not. There is work by some community members to get UniD3 and similar contracts executable through the same model with an NFT. The difficulty right now is that an NFT is minted with a random ID, and to be shielded into the private balance, that ID must be known ahead of time. And so there's a little bit of complication there, so it's not possible today. The fees are calculated by the cookbook. In fact, the point of this recipe is to focus on what the call is, the cross-contract call, and you won't have to worry about the unshield, the shield, the formatting of the multi-call. You won't have to worry about any of that. The fees are already calculated. So if you were to unshield, let's say 10,000 DAI, right? The fee would be 25 DAI. And the input to the next step would be 10,000 minus 25. You don't have to worry about that. You just worry about, hey, I have a step. I can do the math for any input. And then when that step is used in a recipe, the inputs are already calculated for you. That's what makes the cookbook more convenient then.
Are there any ways to optimize fees?
Yes.
yeah, I guess so. Am I coming through fine? People hear me?
No, not to me.
No? Okay. All right, I'll lean over. I'll lean over here. That's fine.
Questions about optimizing fees?
Yes. So the questions is any way to optimize fees. So I guess like the point of the cookbook is that it does all the calculations for the exact amounts behind the scenes, which is why you need to, in your recipes, you're specifying your input ERC20s, your output ERC20s. So that way the cookbook code can actually go off, figure out the exact amount that you need to unshield, and like not unshield more, so you don't end up paying more fees. There is some work by contributors on an update to the Railgun contracts, which would allow the adapt contracts to, like you could provide an allowance to the adapt contract, and then the adapt contract on execution can go and say, well, so let's say you're doing a Uniswap V2 trade, right? You only know the exact price and the exact consumed tokens on execution. And so you'd be able to, like, give a maximum allowance to the adapt contract. The adapt contract will then go and check what the exact execution price is and only request those tokens. And so that would bring the fees down, and you know the other side. Something's happening. Yeah, and the other thing that would allow you to do is, you know, if you know that the transaction's going to revert, you can just simply choose not to unshield anything. So you know, in your adapt call, you'd like check, well, is this transaction going to revert? If it is, I'm not going to unshield anything because I know like there's no point, and I don't end up paying any unshield shield fees that way. Yeah.
There's another, I guess, option that's been theorized, hasn't been built out yet, which would be to use an NFT-based account. What's it called? An NFT-owned account?
Yeah.
ERC.
Yeah, like the NFT like owned the backpack standard. I forget the exact ERC number, but
An NFT can own an account that you can use to hold a set of assets.
So I think the ERC titles like NFT backpack accounts or something, but essentially it allows an NFT to have like a Gnosis safe, for example, like a multi-call that you can then like perform actions from. So if you're like entering and exiting a position, if you didn't want to pay the fees on like every entry exit, what you could do is you could enter the position into an NFT because you don't pay fees on the NFT. You enter the position into an NFT, and then when you want to exit the position, you liquidate the NFT, pull the resulting assets back, and you're only paying the fees on the assets on either end. But it doesn't really lose you any privacy because you're still sort of entering, exiting the same position that people can like see happening.
You would cut your fees in half because shielding an NFT is 0 fee.
That's a question.
Yeah.
Cool. So we're going to look quickly at the structure of the step. So, you know, the setup data for the output. Basically, we're passed in a set of inputs, right? This could be a really multifaceted recipe. It could add liquidity. It could also swap at the same time, just for sake of example. And so we don't necessarily we don't have a guarantee that the input will be only token A and token B, right? So there's code here to filter out and make sure that we have token A and token B, and to figure out the amounts of each, and then also provide us unused amounts that we can pass as outputs. This step itself will be entirely validated. If you forget one of the outputs, this code will throw an error. And so that's pretty nice about kind of the formatting here as well. Once we have that, we get the validated amounts. We can calculate the minimum amounts based on the slippage value. We get the relay adapt contract, which is going to be actually the to address. Relay adapt, again, will perform the add liquidity action. It needs to be on the receiving end of the LP token so that it can shield it back into the private balance.
So for context, relay adapt is It's a multi-call contract that wraps like all your calls alongside the unshield and shield phase, unshield and shield steps into and out of your private balance at either end.
Each of the so we're going to spend token A, we're going to spend token B, as I mentioned earlier. Those will be, spent. They won't be in this account anymore. We have an expected amount of the LP token, again, based on slippage. And the output amount will have an expected balance and a minimum balance. This is important in order to, at the end of the recipe, to show a user who's going to execute it what the minimum amount they will receive is. Right? This is something you'd probably see commonly in Uniswap or when you're adding liquidity. It will tell you the minimum amount received based on the slippage that you have provided. These values are all, we don't have any hard-coded numbers in here, right? And we don't pass in any hard-coded numbers. The step itself is pretty abstract, and it depends on what the inputs are, so that it can be formatted in any order. When we go into creating a recipe, that part gets a lot simpler, actually. So add liquidity recipe. Oh, not this one. The Uni V2-like add liquidity recipe. That's what this is called. It has a recipe config similar to the step config. We pass in basically token address and decimals for token A and token B. What are the two tokens we need to add liquidity for? This does need a provider, like an RPC provider, because it will need to issue view calls to know how much of token B and token A we need to, or kind of what the price is based on their values. If you're creating a recipe, there's a call for supports network and pass in a network name. So you could say, if network, if network is Ethereum, return true, otherwise return false, right? This is where you can isolate, we only want to support Ethereum with this recipe, for example. We have a step that's a helper here to get the liquidity data. This is pulling the data that's necessary for the step based on the amounts that are required. This is another helper function. It gets a little complicated again with the math on the calculation there. But this is the important part that you'll need for every recipe. A recipe is a set of steps that happens in a certain order. For example, we will always need to approve token A and approve token B in order to add liquidity for A and B. These can all happen in a multi-call. They happen in a single transaction. Typically, in a public wallet, you have to issue an approval as a separate transaction to your swap. But this will happen all in conjunction in order. If you haven't approved these tokens, this again will throw an error because it requires approved tokens in order to add liquidity. This right here is the entire recipe. And in context, it will actually have an unshield step, and it will be surrounded by a shield step as well. This is kind of what the entire multi-call will look like in terms of like the populated transaction. At the end of the day, it'll have a to and a data field for an unshield. It'll have a to and data for approve A, approve B, add liquidity A and B, and then shield LP token. This right here is what is formatted by the cookbook. There's to and data fields for each of these, set as an array, set as a multi-call, forwarded to the relay DApp contract. When it executes, it's against a private balance. It does an approval or two approvals. It does the add liquidity, and then it will shield the LP token back. So this is a very complicated recipe, as opposed to some of the things I've heard people talking about for the hackathon. I would encourage you to start with something simple. I know that somebody who's been talking to us at the booth wanted to start with a recipe that simply unshields and then deposits those tokens into a smart contract and shields nothing at the end. That's a really simple start and something to get you going. If you're creating a recipe, the order of operations would be first create the add the ABI and the contract call. Second, add a step with some basic action, add the recipe, and then you'll want to verify that they're working through unit tests. You can follow, for example, the unit tests look a little bit complicated, but they're really just checking the outputs are what we expect. For example, should create Uniswap v2 add liquidity recipe, right? This will use the code we just looked at for the recipe. We pass in an input. These are the ERC20 amounts for token A and token B. We don't need NFTs. Again, this is an empty array. It'll kind of just go throughout the transaction. This is the only call we really need is recipe, get recipe output. This will run all the steps. It will validate the inputs and outputs. And then the rest of this test is just expecting that the outputs from each of the steps have the values that we expect. So at the end of the day, again, the code looks pretty long, but it's very simple, just checking that the math is correct. Once you get that far, you can run a fork test. Probably follow what is happening in another fork test. A fork test will actually fork Ethereum, for example, through an RPC. It'll take this current state of Ethereum and it will run your contract calls against that without spending any gas, right? It forks Ethereum at that block. You can deploy a new contract and then issue a relay adapt call against that new contract. You can do that all through the cookbook with these fork tests. And at the very end of that, this is really it. Again, get recipe output, and then we execute recipe steps right here. At the end, all we need to do is expect that for this test, for example, we're going to expect that the LP token in my private balance, or the LP token appeared in my private balance and it has the right amount. That's basically the entire thing, right? We want to execute, we want to add liquidity, and then at the end of this entire recipe, we should have an LP token in the private balance. So this test, I mean, it's 100 lines of code or something, just kind of set up. This is what's running it, and then at the end we say, is there LP token in the private balance? And that'll run. So I think wanted to ask if there's any kind of questions on the cookbook stuff, and then Kai's going to talk a bit about private governance and how one might set up a system like that. We got a question in the back there.
I just want to add real quick for the recipe, you don't need to do the shield step or the unshield step, right?
That's right, yeah. So I had shown those, where was it? Back down here. As the cross-contract calls that get sent to relay adapt, this one is handled by the cookbook, the shield, and the unshield. So your recipe only needs to have the kind of the inner contents. Unshield, like do some stuff, and then the result is shielded automatically. Oh, one moment. Oh, got a mic.
One recipe works.
Yeah.
Consists of a few steps and maybe some steps they don't connect with each other, don't connect the execution. And if one step fails, it continues on another one, or it will stop.
Yeah, that's a good question. So I guess it was two questions. The first is, can a recipe have, different steps? They can. Well, they certainly can have multiple steps.
Yeah, if some of them it fails.
If a step fails, then what happens, right?
Yeah.
So there's two pieces here. The first is if you construct your calls incorrectly, right, or you give it invalid inputs, typically with one of these calls, you will estimate the gas, how much will it cost for this transaction. That will fail, right? It will revert. The call will revert, and you won't ever submit it to the blockchain, right? So you'll know that pretty quickly. You'll certainly know it in the unit tests, in the fork tests. And so you won't actually have to submit a transaction to know. If a transaction fails because of a logical, not an error, but because of slippage, right? Slippage is a reversion. If the price action changes a lot and the call will revert, it won't add your liquidity. In that case, the call will revert. The way that it works with Railgun v2, the call will revert, but the unshield and the shield steps still happen. And so the difficulty with that is you still pay gas, right? Just as you would with a call that reverts, you pay gas, or a slippage. You pay gas with that.
Yeah,
right?
yeah.
You would pay gas in a public setting as well. With Railgun v2, you actually get hit with the unshield fee and the shield fee because the full call will be successful, but the part in the middle will revert, right? So you won't actually add liquidity to anything. You get fees on either end, so it's not the best setup. Contributors have been working on Railgun v3, which comes out in a couple months, I think. It's going through audits and other things, which will remove the fees in case of the revert. So it's going to be a little bit safer to use.
No, it just terminates everything. Besides actually.
Yeah, right now it terminates the call. Yep.
So thank you. You showed us how a recipe consists of steps, but could you actually show when you are providing PDT, the action? Can you actually show it marketing mode?
Sorry, show.
For the demo at the end, is that what you're asking? I mean, I think we'd probably be fine with if you could demonstrate it working through the unit test and all, and in fork mode. That's I think that'd be acceptable as a demo. Yeah.
It might be it seems nicer to have a UI, but if you have a fork test running and showing that a private balance changed in some way, that's probably further than most teams will get, I imagine. And it demonstrates that the recipe is 100% working, right?
Yep.
That's way cooler.
That's cooler than UI to us nerds in the room. So
Yeah. I think we might be out of time for governance.
we want to mention a few things about the government.
All right. So we've only got 5 minutes left, so I'll have to make the governance a bit quick. So the other prompt, besides the DeFi, or just a general catch-all DeFi, one was doing private governance. If you look at the prompt, it does go into a fair amount of detail in where you can get what data. But as an overview, essentially there's three things that you want from private voting, right? So one, or just voting in general, right? You want the validation of eligibility to vote. You want to make sure that someone can't take their credentials as valid to vote and vote twice with them, and then you want to make sure you actually calculate the outcome, right? So with private voting, the way the part that RAILGUN would play in a private voting system is on the eligibility to vote side of things. So let's take an NFT, for example. You've got, do you want to pull up the like get Merkle proof thing? Yeah.
Oh, sure.
Yeah. So if you've got an NFT, for example, in your private balance, that is within a cryptographic accumulator within RAILGUN. And so you can actually take that accumulator, put it into a voting circuit, and run proofs against that. You know, something, if you're like building this for the hackathon, something you could do to like kind of shortcut that would be to just grab the RAILGUN transaction circuits, strip out the actual outputs for it, and leave the like, you know, eligible to spend bits in there, and replace the outputs with like your voting outcome. So you're like, you know, cast a yes vote, cast a no vote. But essentially, you know, balances within RAILGUN are stored as UTXOs. And so what you can do in your circuit is you prove that, well, I have a UTXO, let's say anyone with a particular NFT collection can vote, right? I can go and prove that I've got a UTXO within RAILGUN for a particular NFT. And that means I'm allowed to vote. And then, you know, of course, you want to make sure that the UTXO isn't spent, so it's valid. You check the nullifier on the RAILGUN contract hasn't been used yet. And then the second bit, you know, making sure you don't vote twice. You'd have your own like application-specific nullifier, so that just essentially is like a value that you calculate after the action. That's, you know, kind of unique to your vote credential. And so if you see this value twice, you know that someone's trying to double vote and you reject the second vote. And then the last one, I mean, I guess it depends on what you're trying to do. I guess for the hackathon, people are going to want to stay fairly simple, so you might want to just output a binary yes or no and tally up the votes at the end. I mean, I haven't had, don't have a huge amount of time to go through things, so you might want to catch me at the desk, on the RAILGUN desk later, if you've got questions, if you're hacking on it. Yeah, we've got like a bit of code examples to show, you know, when you spin up a RAILGUN wallet using the wallet SDK, you can go and fetch the Merkle proof from the wallet SDK and then use that in your voting system to actually execute the votes. We can go through like where to fetch all of those, what functions to call. Yeah, you grab me at the booth later. It is 12 o'clock, which means there is it pasta? There's lunch. There's lunch at the restaurant, so maybe we don't want to keep you from that for too long. Well, we'll hang around here for a bit as well if people want to ask questions.
Yeah, thanks for coming, and we'll see you at the booth over there.
Yeah.